Okay, this is section 1A, and this is on explicit formulas for sequences. Again, there's no journal while you're preparing for the test, and this is a really important section that will be showing up throughout the year on tests. Okay, sequences are a different type of function. They are a function, but it's a little bit different because it's called discrete, and we will talk about that in a minute. They are all about finding patterns, which is the basis of most math. This will cover learning target 5 and 12. And the whole reason we talk about sequences is because it covers subscripts, which is something that you need to go over because it does show up a lot in math. It involves practice with formulas. It is an example of a function, and it helps us identify patterns, which is a really essential problem-solving skill. Okay, so what is a sequence? Well, a sequence is a function, like I said, whose domain is all positive integers. All positive integers. So where does it start? In the x column, it starts with 1. And it goes 2, 3, 4. Okay? We don't have 0. 0 is not positive. There's no negative terms. And notice there's no half. So in this x column, we are limited to the 1, 2, 3, 4, your natural counting numbers. And then each item in a sequence is called the term of the sequence. So the first term could be 2. The second term could be 4. The third term could be 6. The fourth term could be 8. This is an example of a sequence. Okay? It is a function still because the x's will not repeat. Because it's the positive integers, it will go on. There will be no repeat in the x's. Let's look at the example here on this activity. This is in your book. The collections of dots below for the first 5 terms of a sequence of triangular arrays. The number of dots in each collection form a sequence of numbers, okay? So this is my first picture. We call it my first term. Term number 1 has how many dots? 1 dot. This is my second term, because it's my second figure. So the second term has how many dots? 3. The next one is my third figure. The third term has how many dots? 3, 4, 5, 6. The fourth term has how many dots? 10. The fifth term has 15. Okay? I could go on and draw these figures if I needed to, but I don't really need to. I see a pattern here. I have 2 that's added into this one, then I'm going to add 3, then I'm adding 4, then I'm adding 5. So to this, I should just add 6, which would be 21. Then I will add 7, 28, 36, and 45. If you needed to draw the picture, you could. They love to ask problems like this on ACT, the first question. They usually like to have a question that looks like this. And you could solve it by drawing pictures if you need to, but if you can find the pattern, it'll make it a lot quicker. So step 1 was to complete the table. We did that. Notice that after the first term of the sequence, each subsequent term adds a predictable and increasing number of dots to the previous term. Use this fact to complete the table, and we did. This process can continue for as long as you want. You can even think of it as going on forever, because I could draw bigger and bigger triangles if I wanted to. Explain why a set of ordered pairs describes a function. And why is this a function? Because I will always have different numbers in this x column. I will never have a repeat. So for each value of x, the 8th term will always have 36 dots. It will always be that way. It will never give me a different number, so that's what makes it a function. Okay, subscripts and indices. There are different ways and shorthand way we write these. Instead of function notation, a lot of times with sequences we use subscripts. So instead of writing T of 3 for the third term, which you can, there's nothing wrong with doing that, usually we write T little 3, and that means the third term, and we call it T sub 3. So we usually, when we have sequences, we do use subscripts. Okay, an explicit formula. An explicit formula is the pattern, a shortcut, a formula we can use to find that 100th triangle without actually drawing it. Once the pattern is discovered in the sequence, the formula that can be written to find the nth term, basically any term, the 100th, the 13th, the 52nd, you can just plug it in and then you will be able to tell how many dots would be in that 52nd triangle. That's called an explicit formula. A discrete function. I told you before that these are an example of functions, but they are discrete. The reason they are discrete, and you did learn this last year in geometry, discrete geometry, if you remember, was geometry that just had a bunch of dots. The line looked like a whole bunch of dots in a row. Do you guys remember that? Discrete means kind of separated or dots. So it's going to be a function that when you graph it, it's going to look like dots. We do not connect the dots. And the reason being for that, going back to this example here, when I graph it, 1 would be 1, 2 is 3, it's going to kind of go on like this. I can't connect the dots because there's no 1.5 term. It doesn't exist. There's just 1, 2. So when I graph it, there's just going to be a bunch of dots. I cannot connect them. That's what discrete means. The domain is a set with, you can list it like this, the set of numbers 1, 2, 3, forever, or you could put the set of natural numbers. You could do that if you wanted to. We talked about the different types of numbers earlier this year. Okay? So, moving on. This is an example of an explicit formula. Consider the formula t sub n equals 3 to the nth power minus 4. Assuming n is greater than or equal to 1, because remember we can't have 0 or negative terms, what are the first 4 numbers in the sequence? Basically they're asking when does n equal 1, what is it the term, when it's the second term, what is the third term, and what is the fourth term. We want to know what the values are. So we're going to plug in a bunch of things here. T sub 1 will be the first term. Plug in n is 1. 3 to the first minus 4. 3 to the first is 3 minus 4 is negative 1. The first term is negative 1. Now some people might be crying foul here. You're like, wait, you said you can't have negative terms. I can't have a negative term number, but I can have a negative value for that term. Because an example of a sequence, negative 2, negative 4, negative 6, negative 8. That's an okay sequence because the first term is negative 2. The second term is negative 4. So if I made an XY table for this, which is very small, 1, 2, 3, the first term is negative 2. Second term is negative 4. Only the x's can't be negative. The y's can be negative, and that's okay. So t sub 2, 3 squared minus 4. 3 squared is 9. 9 minus 4 is 5. T to the third, t sub 3, excuse me, is 3 to the third minus 4. 3 to the third is 27. 27 minus 4 is 23. And the fourth term, t sub 4, is 3 to the fourth, which is 81, minus 4, 77. So what are my first 4 terms? T1 is negative 1, t sub 2 is 5, t sub 3 is 23, and t sub 4 is 77. Okay? How about t sub 10? What does t sub 10 represent? That represents the 10th term. That'll be 3 to the 10th minus 4. That's a definite calculator problem. I think it is 59,045. Okay? And next example. Alfonso, he has invested $750 for 1 year at 8% annual interest. They're giving us the equation T equals P times 1 plus R to the T, where T is the total principal and interest combined in the account. P is the principal, which is your starting value, and R is the interest rate divided by the number of times interest is compounded. T is the number of times the interest is compounded times the number of years. This is a really confusing formula here. Okay, so we're going to be really careful. 750, that's what he's investing, so that's my P. P is 750. 1 year at 8% annual rate. So R is the interest rate divided by the number of times compounded. We don't know about that yet. And time, we don't know about that yet. Oh, it says 1 year. So time is 1 year. Number of times, the number of years to find. So we need to find out how many times it's compounded. Well, let's look on what they want us to find. Remember, P is 750. That's the only thing we really know. Okay. If the interest is compounded semi-annually, that's what we were waiting for. Semi-annually means 2 times a year. How much will he have at the end of 1 year? How much will he have at the end of the second and third year? And how much at 10? Okay, so let's figure out how much you'll have at the end of 1 year. So T is, principal is 750 times 1 plus R was the rate divided by, R is the rate divided by the number of times it's compounded. So R is going to be, the rate was, well, I went past it again, 8. So 0.08 divided by 2, which is 0.04. So rate is 0.04. And time is the number of years times the number of times the interest is compounded times the number of years. So in this case, time is going to be 1 times 2, which is 2. Okay, so T is 750 times 1.04 squared. And what do we get? $811.20. Type that in your calculator. Okay, now the second year. So now we're kind of looking for the second year, T sub 2, let's say. Well, 750 is going to stay constant. This 1.04 is going to stay constant. The time is going to affect this. This was 2 times 1 for 1 year. Now it's going to be 2 times 2 for that second year, which is going to be 4. 1.04 to the 4th power. And now we plug that in and we get $877.40. How about 3 years? We'll go over here, that third term, 750, still, 1.04. This time I'm not going to take 2 times 2, I'm going to take 2 times 3. So I'm going to plug in 6 as that exponent. Looks like I get $949 even. And you can see what's changing here. The first year it was 2 times 1. The second year it was 2 times 2, 2 times 3. So the 10th year, so T sub 10, will be 750 times 1.04, 2 times 10. That'll be 20 there. Plug that in and we get a whopping $1,643.36. Okay, this is an example of a sequence. We didn't really use the sequence notation except when we were writing what term we were looking for. But you can't have half years in this situation, so that's why they use this as an example of a sequence. Okay, holy cow, that's it for the chapter. You guys need to start this homework and start thinking about that test.